Today, we started with quantum sensing, how to image brain functionality with a quantum magnetometer by Smeja Knappe. Now we will continue with the third session of quantum key distribution by Aeysha Khalique from QWorld and NUST in Pakistan, and continue with quantum computing, algorithms, and programming with Gibran Rashid. I would like to point out for tomorrow that 1.5 hours before the live session starts, there will be a 30-minute virtual office hour hosted by our partner CQ Tech, Taha Ruaba and his team. And they will do an excellent job in answering all your questions on Q-bronze, Q-nickel, QKD, the basics of Qiskit and Cirq, quantum mechanics, and more. Then tomorrow we will have a session on quantum sensing from a different perspective, how to take a systems engineering approach to be successful in this field. And we will have the fourth session of quantum key distribution and Q-nickel tomorrow. I don't want to delay you longer, Aeysha. Please bring up your slides.
Today's lecture would be on QKD with noise. And in this, I will tell how to do information reconciliation, privacy amplification, and then attacks by adversaries. So it goes like this, that so first we knew that if the qubit error rate is if qubit error rate is 0, then you just go ahead with keeping the key. If it is not 0, then you would be doing the further thing, right? So if it is qubit error rate is delta, what we called it, and if it is equal to 0, then I'm sorry, what happened? It is can I just close it? I don't know. Okay, so qubit error rate is no, sorry. So if qubit error rate is 0, we just go ahead with the protocol. If qubit error rate is not equal to 0, then we have to do the information reconciliation, which is actually the error correction, right? So we do the error correction here. And in fact, we learn certain protocols in here, which are the cascade protocol and the parity check. So we have cascade and parity check stuff in that. And then, of course, while doing the error correction, we give some additional information to Eve, which increases her information. So we have to do privacy amplification. So after doing this, we eliminate Eve's information from here. So we eliminate Eve's information in privacy amplification. And this is what we will learn, how to do that, Eve's info. And then, of course, we will see that what additional advantage Eve can have. So there are certain attacks that she can advantage of your imperfect resources, and she can do certain attacks where she can really take advantage, such like the photon number splitting attack. So that one I would like to discuss. So let's see that, I'm sorry, it just, the slides got mixed up, did it? Okay. Okay, let's see. So let me just revise the BB84 protocol. So BB84 protocol went like this, that it is that the start with there are 4 basis states, 2 bases, and there are 4 states in them. They mark each one of them with 0 and 1 bit. So these two, this one is marked 0 and this one is marked 1. Green is 0, blue is 1 in the bases, diagonal bases, and yellow is 0 and purple is 1 in the horizontal vertical bases. So Alice chooses the basis set by tossing a coin. She then chooses a state, sends it to Bob. Bob, on the other hand, is sitting with his basis states, and he then selects the state basis set, and then he measures it. If his basis exactly matches with these, they're they record the bit value, right? According to these assigned values over here, their bit values exactly match, and he keeps the bit sequence. Then after all the bits have been transferred, they will compare the bit sequence, and they will compare the bases, they will announce the bases, and then they will keep only those cases in which their basis set matches, right? And in this way, in the sifted key, after the announcement of bases and throwing away all the cases where bases did not match, they will be able to have a key which exactly matches in both the cases. And then, of course, in the case of Eve can also be there. So when Eve is there, she will be able to, the headings got sometime mixed up. Let me just arrange them. Okay, I'm here. And so there, then if Eve is there in between, she will have her own basis choices. And say if she uses the same basis as Alice and Bob do, then she will not introduce any error and she will gain the full information. But if she uses the wrong basis, then of course she will introduce the error in 50% of the cases, and she will gain no information in this case, because she's not sure that whether she has got the right bit value or not. So she gains 50% information, and she introduces at least 20%, 25% errors, right? In this sort of an attack. This is called the, this is a simple attack, which is the, in which she's just measuring and sending it to Bob, right? So Eve's information in this case is equal to 50%, and the errors that she introduces is equal to, delta is equal to 25% in this case. So then what Alice and Bob do, what we do in the QKD protocol next is this, that they do the homogenization, which means that they randomly commute all the disturbance, and then they do the qubit error rate estimation, which means that they randomly select half the qubits, which are called the check bits, from the sifted key, right? And then they announce the measurement result, which can be 0 or 1. For those half selected bits, they announce the measurement result, which means the bit value, right? So they're announcing their key for that. The fraction of the cases in which the result differ is in fact the qubit error rate. It is called QWorld, which is actually the qubit error rate. So the error rate in the error rate that simply means that number of qubits that are wrong in compared to the total number of qubits, right? And then they discard all the check bits. Why they discard all the check bits? Because they have been the 0 or 1 values have been announced for that, and now everybody knows about them. So they discard all the check bits, which means that they have discarded half of the key in this case, because they have selected half the qubits in the beginning. So if the qubit error rate is very high, then they would simply abort the protocol, and if it is low, then they will do error correction and privacy amplification with 1- or 2-way classical communication to the remaining qubits. So the remaining bits, sorry. So keep in mind that once the qubits have been transferred and the bits values have been announced and everything for the error correction and everything. So now everything is classical, right? So there are no keys classical. So whatever error correction and privacy amplification they have to do, these are all the classical methods. So they will be using only those the known classical methods for that. Now, in order to go ahead further with it, we take a very pessimistic approach, and the pessimistic approach is this: that the first thing is that we attribute all errors to Eve, right? All errors are attributed to Eve, which means that they may be because of the channel, they may be because of the loss of the photon through the channel, they may be because of the flip of the photon while going through the channel. But we say that actually whatever errors are there, they are because of the Eve. So we do not know whether they are because of the Eve or because of our channel or anything, or our device produced them wrong. But we say that all errors are due to Eve, and we have to now eliminate Eve's. They are all included in Eve's information, and we have to exclude her information from there. Okay, so and the second thing is that we assume that Eve has all powers allowed by the laws of physics. I'm sorry, this pen is. So we assume that Eve has all powers allowed by the laws of physics. Eve has all powers allowed by laws of physics. And while Alice and Bob are restricted by the current technology, right? So we are assuming that they have the powers that are allowed by the present day technology, but Eve can do whatever laws of physics allow, right? So whatever is not possible today, we assume that she can even do that, but it should not just violate the laws of physics. So Alice and Bob are restricted by the technology, by present day technology. Okay, so this is the approach that we will have while calculating that how much qubits would be lost during the error correction and the privacy amplification. So I said that here that if the qubit error rate is very high, the protocol is aborted, and if it is low, then they have to apply the error correction and privacy amplification using one-way or two-way classical communication, right? So what is meant by high and low qubit error rate? There was a question last time as well in the yesterday's lecture, that at what point we say that we cannot do anything, you cannot have a secure key while doing any method of error correction and privacy amplification. So there are some known bounds for that. For example, for this BB84 protocol, we have a lower bound on one-way classical communication. So by one-way classical communication and two-way LOCC means that in one way, only Alice or Bob announce something, right? And in two-way, both of them announce something. So in the first case, in one way, when one of them announces something, then less information is revealed, right, while doing error correction. And when both of them announce something, then of course more information is revealed in that case. So we know that there are certain known two-way classical communication protocols, which is the Blow-Go-Sven protocol. And so we know that the bounds on which they work, if you use one-way classical communication, then BB84, it works on 11.37%. Of course, you're revealing less information, but you have less power as well. So you can correct less percentage of errors. But if you do two-way classical communication, you and both Alice and Bob announce something, then you can correct more errors, which is up to 20%. And then which means that you have more power than the one-way classical communication in that case. And we know that intercept resend attack that I just described again, and which we did yesterday, that somebody is intercepting, measuring it, and then resending the original qubit. So in that case, the error introduced is 25%. And if does the optimal individual attacks, then it becomes insecure for the two-way classical communication. It becomes insecure about 30%, and which means that Eve can go up to Eve can introduce more errors compared to the intercept resend attack in this case. So what are these optimal individual attacks? So what does Eve does? Eve attacks each flying qubit separately, right? And she but optimizes her attack in such a way that she gains more maximum information from that. And she tries to formulate her attack when the bases are announced in that. In the general coherent attack, so she will keep all the what she will do, she will keep all the flying qubits together in the general coherent attack, and then she will devise a combined attack on all of them, and then send them one by one to Bob. And in this way, of course, she can it becomes insecure above 25% in this case. So then Alice and Bob, of course, these are the bounds that they will be having using that. And in this case, this is the 25% which Alice and Bob can correct with the BB84 protocol. So in the information reconciliation, what do? They have to correct the errors now, right? So it is in fact the error correction, the information reconciliation, right? So in the error correction, what do they do? First thing is that they can use the parity check method, right? So what is a parity check? That if there is a random string, for example, it is 100 1100, and you calculate the parity of it, which means that it is an odd parity if it has It is an even parity if it has equal number of zeros and ones, and it is an odd parity if it has unequal number of zeros and ones. Okay, so this string 11001100 is an odd parity string, right? So its parity is 1. So its parity is equal to 1. And for example, there is an error in it. For example, what Alice sends is this. This is what Alice has, and there is an error. And she says that the parity is 1. And what Bob receives is in fact with an errored 1. And he receives this, which is 1. There's an error, for example, in this one. So it is 101. In fact, it would be, let me take to be the so this 0 would go to 1, and this is 1 1, and this is 0 0. So there are so there are now 4 ones, and there are 3 zeros, and in this case the parity would be again 1. So it is 0 plus 0 is, so it is 1 plus 1 plus 1 plus 1 is 0, and then plus 0 plus 0 plus 1 is again 0. So its parity would be equal to 1. But what they can do, in fact, is they can append a parity bit with it, right? So what do they do is that they append a parity check bit with it. For example, for 1 bit of information, what would they do? So I just go ahead here. So they append a check bit, parity check bit, and so for 1 bit of information, so for 1 bit of information, they will have, for example, it is 1, right? So they append a parity bit, which is, and make it, append a parity bit, and make it 1 to it. So now what they have is this 1 1. Okay, so with 1 bit of information sending, they will have 1 1. They will have 1. Okay, so now if you do parity check, so it should be, it is 1 plus 1, addition modulo 2 1, right? 1 plus 1 mod 2, which means add them up and divide them by 2, and your remainder is the answer. So they are doing this 1 addition modulo 2 1, which is 0. So the parity check gives that it is 0, right? So if there is an error, right? If there is an error, then the parity check would be the parity bit. Of course, they append a parity bit, and then Alice sends both the original bit and the parity bit to Bob. So if there is an error, right? So there can be any sort of an error that your original bit remains the correct thing. Your original bit is 1, and I'm sorry, I think this pen is making some. So if your original bit is 1, and your original bit goes to 1, and then with error, without error, of course, it's 1 1. Okay, and but with error, it can be anything like so with error, it can become, the first one remains 1, the second one can flip, right? So there's an error in it, so the second one flips. So it can be 1 0, and it can be, the first one flips, so it can be 0 1, and both of them flip, right? So it can be 0 0. So these are the cases with error, and this is the case 1 1 without error. So if it is 1 1, then the parity check would reveal that that is, you take the addition modulo 2 of the 2. So the receiver will say that my parity check gives 1. And if it is 0 1, then of course again parity check will reveal the value to be equal to 1. And if it is 0 0, both of them flip, then in this case the parity check will give the value 0. So in this case they detect that there is an error, right? And in this case they will not detect that there is an error. So the error is detected, and in the lower case the error is not detected, right? Because it gives the same parity value as in the case of the correct values, which is 1, 1. So error is detected in fact in 66% of the cases, right? 2/3 of the cases. So in this case, if you append a parity bit, the error will be detected only in case of the 66% of the cases. So what they do is they have to do something else. So they have to then use certain different methods. So they can try cascade protocol in order to correct the error, right? So they try the cascade protocol. So in case of the cascade protocol, they do what? They divide it into, they have, of course, all the bit sequences. So they take a block of these sequences, but before they shuffle the bits by applying random permutation, right? So why they do that? In order to distribute the errors uniformly among all of them, right? So they shuffle the bits by applying random permutation, okay? So this is what they will do. And then they will divide, for example, this is they divide the bit string into equal blocks. They divide bit strings into blocks. Okay. So which means that, okay, this is a bit, this is a bit, this is a bit, this is a bit. They divide it into block, bit, 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 another block, bit, 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 another block, and so on, right? They divide it into many number of blocks. So divide it into sub blocks over here. So in this case, then they would then compute the parity bit of each of the block, which means that they add all of the bits in there, and then now they calculate what is the value of the parity bit, right? As I said in the beginning, they will announce the parity bit. So they compute the parity bit for each of it, right? Take the addition modulo 2 in each case. So they do the parity bit. Compute the parity bit for this, parity bit for this, P1 for this, P2 for this, P3 for this, and so on. And then they announce this value of this parity bit for each of this block, right? So they announce the parity value. So they announce the parity value of each block. Okay. So let me add a, I don't know how to get rid of this. We are here, so we add a page, and then we are, so they have announced the parity, the value of each parity bit of each block. And then if the parity matches, so then they say that this block is clear of an error, okay? So if parity matches, then they announce that the block is error-free. So they accept that the block is error-free, okay? And otherwise, if the parity bit doesn't match, then they accept the block that it has an error, okay? So if parity bit, if P doesn't match, the value of the parity bit, any Pn, right, doesn't match, then that nth block has an error, okay? Okay, so far so good. And if it has an error, then they divide it into further subblocks, right? They divide it into further blocks. For example, this one had an error, the number 2, 1. Then they divide it into, again, 2 smaller blocks, and then compute the parity value of each of the blocks. And then if there is an error, then they will be computing it, right? And before dividing it into further subblocks, they will again randomly permute the whole block, right? The block for which the parity bit didn't came out to be correct. And they can also do it like this, that they again mix up everything and then divide it. So after seeing where the error is, they will then repeat all of this many times. That is randomly permuting again, so that error is again redistributed, and then they will be computing the parity bit of each block, and so going on so far. So going on like that. And in this way, of course, in each parity block, as I said earlier, if there is one error, of course, there will be error, they will be able to locate it. But if there are two errors in one block, then that cannot be located. So that is why they have to repeat this process again and again in order to find the error in the block and in order to locate it, okay? So in fact, the cascade protocol fails if the error rate is greater than 0.25. So this is the limit of the cascade protocol, that where it can work, fails for delta to be greater than 0.25, which is 25%. Okay, so then the cascade protocol doesn't work. And so now what is happening? And then of course, they have to compute, they have already computed what the error rate was in the beginning. So if your error rate is very large, then the block size should be small so that they can look at it. So that in one block size, there is a chance of one error only, right? So for large qubit error rate, there should be a, implies you have to make a block size small, right? So there should be a small block size. And if the qubit error rate is small, then there should be there can be a large block size. And of course, you want to make it efficient. So you will take a large block size, and because there is a chance that in one block, there will be only one error in that case, right? So now you are announcing the parity bit of each of the block. So which means that while you are doing that, you are actually revealing some information about the bits. For example, if Eve assumes that she has only made one error somewhere, and her bit value doesn't match, so she knows that there is somewhere one bit is flipped in that case. And if to further divide it, and then some of the information, she knows she can locate where her error is after each of the permutations. So permutations are done by mutual consent, which means that both Alice and Bob know what permutations they are doing, and also the permutation is announced. So Eve also know what permutation they are doing, how they are mixing up the bits. So, so while doing this error correction and while announcing the parity bit value, they are revealing some information to Eve. So which means that while they are doing information reconciliation, which is the error correction, it increases Eve's information as well. So information reconciliation increases Eve's error, the Eve's info, sorry. Okay, so so first they have to do error correction. So whatever information is revealed, it can be revealed to Eve, and then they will be needing privacy amplification for that. Okay, then so they go to the privacy amplification after that. So first they have to do the error correction and then privacy amplification. If they do privacy amplification before error correction, then again during error correction, more information will be revealed to you, and they have to then do the privacy amplification again. What is privacy amplification? Privacy amplification is removing Eve's information, okay? They have to amplify their privacy. So they have to remove Eve's information about the key. So this is what the privacy amplification is. And they would like to do it in such a way that they do not reveal further information to it, and they do not introduce further errors to it, okay? So how can they do that? So let's see what is the simple process, what can be the simple process for privacy amplification. So for example, they have two bits, so they pair up their bits, right? Alice on her side and Bob on her side, but they know which pairs they are, which one is going to be paired up with which bit. So for example, again, they will, for example, in order to do the privacy amplification, they will randomly permute their bits, right? So this is very important, the random permutation, so that everything is reshuffled and the information is redistributed, and it is equally distributed if the bit sequence is very large. So they randomly permute their bits, and then they divide Alice on her side and Bob on his side. So they divide their bits. For example, they pair up their bits. For example, they announce that bit number 1 and bit number 56 are going to be paired up, right? So they announce this, that bit number 1 and bit number 56 is going to be paired up. So Alice on her side and Bob on his side, this is the bit number 1, and bit number 56 is going to be paired up. So it is, if the bit value is 1 over here, and the bit value is 0 over here, then they will keep this bit, okay? And Bob on his side also keeps the bit value, the bit number 1 and bit number 56. So I just leave this to order in order to compute for Alice the, okay, so he also does this. And if and then they would do what? So they will be they just compute the addition modulo 2 of the two. So we assume that they are error free. So both the addition modulo 2 of both the bits should come out to be the same value, right? So for bit number 1 and bit number 56, the addition modulo 2 from both of them, from here and here, it should come out to be 1, right? So they are keeping the addition modulo 2 of the two bits, right? And they're just keeping it. They're not announcing anything. So they are not revealing further information. They compute the addition modulo 2 of this bit, and this bit, and they keep the value, which is this. So this is what they're going to keep, which means that, and then they pair up all of them. For example, they pair up number 2 with bit number 185, for example. And if this is 1 and this is 1, and they are doing the addition modulo 2, they are going to keep the value 0. Bob also has the same. So he has, this is 1 and this is 1. He will be also keeping the same value. So this is what they are keeping. So out of each pair, they are keeping only one value, which is actually the addition modulo 2 of the two, right? So they are not announcing anything. They are not revealing further information. But if Eve has some information about the one of the two, then her information about the addition modulo 2, her information about the key would be reduced in the addition modulo 2 operation, right? So because in this case, it may be possible that she knows one of them, and then she will be, and she doesn't know the other. So she won't be sure what the bit value will be, whether it is 0 or 1, right? So in all the cases where she doesn't know exactly what the other bit is, she will not have no information about the addition modulo 2 as well, right? So in this case, her total information would be reduced. This is how they do the addition modulo 2 of the by doing the addition modulo 2, they amplify their privacy. So and again, the key reduces to half. So again, the key reduces to half the length. So in this case, after the error correction, the key also reduces because they are dividing it up and they are throwing up the bits in this case. If they do that, okay. There's another method of error correction as well, which is useful since we know that how this addition modulo 2 works. So what they can do is they can again pair up in the error correction process. Before doing the privacy amplification, they can make use of addition modulo 2. That is, they can pair up their bits and then they compute the addition modulo 2 of the two, Alice on her side and Bob on his side. And if then they announce the value of the addition modulo 2. If the value of the addition modulo 2 matches, then they will throw away one of the bit and keep the other. If it doesn't match, then they will throw away both. Okay. So let's see how it compares with this privacy amplification process. So I go back to it because this privacy amplification gives us an insight that we can do error correction with addition modulo 2 as well. That is, they pair up again their bits, right? So they bit number 1 and, for example, bit number 4, they pair up, and Alice on her side computes the addition modulo 2 of the two. For example, this is 1 and this is 0. So Alice is here and Bob is here. So this is 1 and this is 0. And they compute the addition modulo 2 and Bob is here, right? So if Alice's addition modulo 2 comes out to be 1 in this case, and Bob's addition modulo 2 can come out to be, if his value is the same, it will come out to be 1 again, right? And they announce this value. They announce this value, both of them. If it matches, then they say that there is no error. So they are again locating one error. If it matches, there is no error. Then in this case, they will keep. They will throw away one and keep the other one, right? While they are throwing away one, because while announcing the addition modulo 2 value, they are revealing some information to Eve, right? So in this case, they will keep one and they throw away the rest. And they will keep one of the two and throw away the other one in order to reduce Eve's information. Okay, because Eve knows that, okay, the bit value, the addition modulo 2 is 1, but she doesn't know which bit is 0 and which bit is 1. So if they throw away 1, Eve will again be not sure that the bit that is kept was 0 or 1. If she already doesn't know exactly the value of the bit. Okay, so they throw away one of them. And if the parity, if the addition modulo 2 doesn't match, for example, for Bob, this comes up for Bob, it can have this to be 1 and the other one to be 1 as well. So in this case, the addition modulo 2 comes out to be 0. And then in this case, it doesn't match, right? So which means that there is an error in it, right? And then they throw away both, because they throw away all the sequences in which they have an error, and they throw away both. And then, of course, this bit string will be reduced to 1 then. And in this way, they can keep doing the information reconciliation in this case. But of course, it is an inefficient method because they're throwing away bits. So this cascade protocol, and which I told earlier, is an efficient method compared to that. Okay, so this is how the privacy amplification and the error correction can be done, right? So this is inefficient, I must say, compared to Cascade 1. And of course, this has to be done before the privacy amplification again, right? In order, because they're revealing some information to Eve. So we talked about information and talked about the attack that Eve does, which is the intercept resend attack, but she can also do some more attacks. There can be one in which there is a man in the middle, right? So there can be a man in the middle apart from the adversary, and he may be talking to Alice and Bob. So first thing, in order to be sure that they, in this case, that Alice and Bob should be sure that they are talking to one another, right? So there should not be anybody in between. All the classical information that they are revealing during error correction, during sifting and everything, there is no middleman, right? So they are talking directly to one another. So this should be important to them. Or if there's a middleman in between, he should be loyal to both Alice and Bob, right? So there should be one thing in all these processes should be there, which is this, that both Alice and Bob should be talking to each other. So Alice and Bob should be sure that they are talking to one another. That they are talking to one another, right? There is no middleman. Okay. But there's much more that Eve can do. There are certain situations in which Eve is at much more advantage compared to Alice and Bob. For example, if we have faulty apparatus, right? So Eve can take real advantage of that. One thing is that this was on the extreme left. This is our source, right? From which Alice is producing the single photons. In the real world case, it is not very easy to prepare the single photons, so there may be multi-photon pulses there. For example, these are the weak coherent pulses. And weak coherent pulses, these are the laser pulses. They have the photon number distribution. This P of n is in fact the photon number distribution. It is Poissonian. So it contains, so there are certain pulses which contain more than one photon. Of course, your P of 0 is the largest, and P of 1 is in fact the probability that there is a 0 photon in a pulse is largest, and probability that there is 1 photon in a pulse is even larger than P of 2 and going on. So it's like that, right? But of course, there are pulses which have more than 1 photon. Then the channel through which the photon is being transferred, it is very lossy. So in fact, the channel efficiency depends on the distance. For example, the channel efficiency here, it is eta t, which is given as 10 raised to power minus alpha L plus C, where L is the distance, right? The fiber length, and alpha is the absorption coefficient. So while going through the fiber, some of the photons get absorbed by the fiber. Okay, and so the channel efficiency decreases, right? It is with a negative sign, so it is exponentially decreasing with the distance. So as the distance increases, the efficiency becomes very, very less. And then also there can be a constant loss in the channel. So the constant loss in the optical components is given by C, right? So it all decreases the channel efficiency exponentially. And then there's a detector. Detector may be faulty. For example, detector can have less than 1 detection efficiency. So your eta detection will be less than 1. So your eta detection is less than 1. And in addition, so eta detection is less than 1. And eta detection is less than 1. And also there are dark counts. What are dark counts? So I call it PDC because I think I'm using this symbol ahead. So there's a probability of dark count, which is also greater than 1. What is dark count? There are certain cases in which the detector clicks even when there is no original signal, right? So there can be thermal photons in the atmosphere. And these stray photons may hit the detector, and detector clicks even when there is no original signal. These are called the dark counts. Okay, so these are not coming from the signal, they're just coming from the stray photons out there. So these things that they reduce the detector efficiency, and of course they will affect how the signal is there. So everybody knows that, right? Everybody knows this experimental setup. Everybody knows that channel has this efficiency. Channel has the source has this efficiency. It produces multi-photon pulses. So Bob is expecting that he will not be receiving all the pulses that Alice is sending, but he will be receiving less. So what he's expecting on his side? So his expected probability of expecting a signal, receiving a signal, his expected signal is this, that if she sends 1 photon, then Bob is expecting that he will receive 1 minus the ones that is lost. So it is 1 minus exponential of minus mu. Mu is the efficiency. Mu is the average photon in the Poissonian pulse, which is over here. This mu, right? The photon, which tells how many average photons are in a pulse. So it is minus mu, and it also reduced by eta detection. It also is reduced by the channel efficiency, right? So Bob is expecting that he will be receiving these many signals, not all of them. So this is what he's expecting. And then, of course, there are the probability that there are multi-photon pulses. So M is for multi-photon, and the probability that there are multi-photon are like this, that there is a summation n greater than or equal to 2. Just a minute. So they have, so if she sends, like, for example, there are pulses, for example, so for those pulses, there are more than 1 photon, so n is greater than or equal to 2, then the probability that there are more than 1 photon is this Pn, right? Which is this Pn, right over here, this one, and Pn, and then of course that there should be the signal is, it produces this much photons, the probability that it produces a photon greater than 1, and also that it is detected. So the probability that it is detected should be, I'm sorry, my pen is creating problems today. So it is the probability that it is at least one of these multi-photons are detected. So how they are going to be detected? So I subtract the probability that not n minus 1 are not detected from 1, right? But 1 is detected. So 1 minus eta detection, and it is the all n minus 1 of them, and this would be then equal to all n minus 1. And this would be, so this is giving 1 minus, and raised to the power minus 1 is giving me that at least 1 is detected, right? This whole thing is that at least 1 is detected. So this probability will depend, of course, on eta detection, and this P of n depends on the probability of the multi-photon pulses in the probability of number of n photons in the initial pulse. And having the multi-photon pulses means that there's more than 1 photon in each pulse, which is Pm, right? And which starts from n greater than or equal to 2. So whichever pulse has number of photons greater than or equal to 2 will contribute to this multi-photon pulses. Weak coherent pulses are the ones which I talk about here, which is this WCP. These are the weak coherent pulses, by which I mean that a laser produces a pulse, right? So it does not produce a pulse in which all the photons are coherent with it, which means that each pulse does not contain a single photon into it, right? So these are weak coherent because we can always produce the laser. We try to produce a laser pulse in which the number of photons in each pulse is very, very low, right? That is why we are calling them weak. If it is a strong coherent pulse, then of course it will be a strong beam, and in each beam there will be there will be large number of photons. We try to keep them weak, so that so that there's a very less probability that there are more than one photon in each pulse, right? That is why we keep them weak. This is what I mean by weak. But of course, this is a substitute for single photon pulses. This is the best that we could do with normal experimental setup available. So this is what I mean by here weak coherent pulses. And then so I hope it's clear now. I think I've answered this question. So if there's any other, let me check. And
yeah, and then a brief repetition what the parameters mean: mu, eta.
Okay, so my mu is mean photon number. Mu is defined as the mean photon number, right? So you have a pulse which can produce, each pulse can have certain number of photons, and this how these number of photons are distributed. So these number of photons are distributed according to this probability, that it is e raised to the power minus mu, mu raised to the power n, and this mu is in fact the mean photon number, the average photon number that I've called it here. So it is the same thing, right? So mu is the mean photon number. So each pulse has certain number of photons, and the probability how many photons will it have, it depends on the average photon number mu, and it's a Poissonian distribution. So it is e raised to the power minus mu, mu raised to the power n over n factorial, right? And you can see that it decreases with each increasing n, because it is being divided by n factorial. And if n is greater than, as I said here, the probability that there is a zero photon is the greatest, because it is equal to e raised to the power minus mu. Probability that there is one photon is e raised to the power minus mu, mu raised to the power n. And mu is of course always less than 1. And then with increasing n, each Pn decreases, right? So P0 is greatest, P1 is then smaller than that, P2 is even smaller than that, and going on. But of course, a number of, there is certain probability that there are more number of photons in that, right? So I hope this setup is clear to you.
Great, let's continue.
Okay, so in this situation, when there are such faulty apparatus, then Eve can really modify her attacks. What she can do in this case is, she can do a photon number splitting attack. What she can do, we have assumed that Eve, pessimistic approach, that Eve is only restricted by the laws of physics, right? So she can have immense power, but laws of physics allow her. What she can do is she can replace this faulty line, this lossy channel, with a perfect one, right? And then, so what this means is that Bob is expecting lesser number of photons. Now her eta t, she makes this eta t to be equal to 1, right? So Bob was expecting this in this case. So P expected of Bob was, P expected over here was equal to 1 minus e raised to the power minus mu, eta detection and eta t, okay? So if she makes eta t to be equal to 1, Bob is expecting less photons, but she is sending almost more. She is sending almost all of them that she receives, right? So apart from the weak coherent pulses that are there, apart from the multiple photons there, she is sending whatever Alice receives from Bob. But what advantage she can really have is that she can do a quantum non-demolition photon number measurement. So this QD means she is doing quantum non-demolition. Pn is photon number measurement. So quantum non-demolition photon number measurement is that she measures the number of photons in each pulse without disturbing the state of the photons, right? And of course, it is possible. Laws of physics allow that. The technology is also available. She can do that. We can say that she cannot have a lossless channel, but in principle she can have. And then she can collect all the photons that Alice is sending to Bob, and then once she does the photon number splitting attack, she keeps the polarization undisturbed. She can then do the splitting as well. So how does she do the splitting? That in each pulse where there are 2 or more photons, wherever there are 2 or more photons, she does a PNS attack, which means she does the photon number counting, do the splitting, that is keep 1 photon with her over here and send the remaining 1 to Bob. And then she waits until the bases are announced. When the bases are announced, she knows which bases Alice and Bob do, and then she measures her photon in the same bases, which means that she exactly knows the bases in each case when on which she has splitted 1 photon. So for every pulse where there's more than 1 photon, she knows the bases exactly. And what is the advantage of having a lossless channel in between? That she can increase the proportion of number of bits for which she knows the basis exactly, right? So this is how she does that. She knows what Bob is expecting. It is P expected, and so Bob is expecting the multi-photon pulses. She can always increase the proportion of the multi-photon pulses like this, that she computes this value, which is delta. It is the number of the multi-photon pulses, which is PM, which we computed earlier, which is this PM, right? This thing, and divided by the P expected. So she just says that how many number of pulses that she can have them on which she knows the basis, and then all the remaining single photon ones, she blocks the rest, right? So she only allows only those single photon ones to pass, which is 1 minus delta number of the single photon pulses. So in this way, she increases the proportion of multi-photon pulses in the total cases which Bob receives. And in this way, she knows that she not only knows the basis for the pulses that are more than 1 photon, but she knows the basis in more fraction of the pulses that are for which the bases are known. And for the remaining one, the bases are unknown, she of course creates a disturbance. So in this case, she has not created any disturbance because she's measuring in the same basis and she knows exactly the value. In this case, she knows the basis, she doesn't know the base, so she will be creating some disturbance, which is T, right? So she's not now contributing 25% error to it, but she's contributing very less error. So Bob and Alice would assume that she knows very less, but she actually knows a lot and knows much more, because these are the cases in which bases are completely known to her, and she has introduced less than 25% in this case. So this is a very fatal attack. It seems fatal because she has now a lot of knowledge about the key string, and she has created very less disturbance. So she's undetected. Alice and Bob can detect her by estimating the error in order to see that how much disturbance she has created, right? So she's undetected and she has more information. So what quantity that we are interested in over here is so what Alice and Bob can do in this case is they can go back to their apparatus, and they would like that they reduce this mu too much, right? So they can then reduce the number of dark counts of that. So they can reduce the number of multi-photon pulses. So the problem is that if they reduce mu too much, reducing mu too much which means that there will be most of the pulses that will be empty, or that will have at least 1 photon. So they reduce mu too much, then there will be a lot of clicks on the detector due to the presence of dark counts. So there will be stray photons more than the original photons, and then that will increase the P dark. Right, so they've reduced P too much. This implies that P dark, the dark count probability will increase. So they cannot reduce the mu too much, the average number of photons in a pulse too much, to reduce this delta over here, so that they can reduce PM, so that they can reduce delta. Right, so this is the hitch in it, that they cannot reduce mu below certain value. So now in this case, that what we are interested in would be that it is the key generation rate that they would be interested in order to see what it would be. So what is key generation rate? Key generation rate is in fact the number of bits that are there, number of bits retained in the end, right? After error correction, after privacy amplification, after sifting and everything, retained in the end, and divided by the total number of bits shared, total number of bits that was sent by Alice, right? So that was shared in between that. This is the key generation rate, which we call as R. So it is not the rate by time, but it is the rate by the number of bits that was sent originally, and how much are left in the end after privacy amplification and error correction, after sifting and everything. So in general, the key generation rate is this. The R is, so we have to, you know that in the sifting process, when the bases are announced, half of the bits are lost, right? So if I assume that the bits is 1, then how much fraction of it will be retained? So half of them are lost, right? And then in general, so we will have that this is the P sifting, which is half, and some of them will be lost in the error correction and in the privacy amplification. So the maximum number of bits that can be lost is in fact equal to this Shannon entropy, right? So this Shannon entropy is H. So I won't go into the detail of that, but just that it is from the classical information theory. Okay, so it is H of delta. If delta is your qubit error rate, then this many number of bits would be lost. It is H of delta, and so there would be some efficiency of error. There will be some efficiency of this error correction process. So it is F of epsilon, which is efficiency. And then there is H of delta, number of bits will be lost in the error correction process. And there will be H of delta, number of bits that will be lost in the privacy amplification process. So there will be H of delta that will be lost in the privacy amplification, right? So actually what we are doing is half 1 minus the fraction of bits that are lost in the error correction, right? So it is a probability that are lost in the error correction, and minus the one that are lost in the privacy amplification. That's how we're doing, right? So this will be the key generation rate. That is the number of bits that are left in band. Now in this case, where she has done the photon number splitting attack, we seem to see that we may be hopeless in this case, that we cannot may not be able to retain any number of bits in band. So key generation rate R should be greater than 0 in order to be, of course, it cannot be less than 0. It has to be greater than 0, which means that number of bits lost that are in this case, sorry, it is, and it is always less than 1. So which means that it should not be that all the bits that have been shared, all of them are lost in error correction and privacy amplification. So you should have certain non-zero rate R, right? So R should remain greater than 0. And in the above case also, we have found, in fact, we did this work some time back during my PhD, and we found that in order to have retained this, so half of the bits are lost in the shifting process. And then there are a certain number of bits that Bob is expecting on his side, certain are lost during the channel efficiency stuff. And this is the P expected that Bob is expecting on his side. And then there is certain ones that are lost in that. So there will be, even there's delta number of bits, so it will be 1 minus delta minus H of delta minus the F of E and H of delta in the error correction process. So 1 minus the number of bits for which the bases are known, and minus F of E epsilon H of delta. These are lost in the error correction process, and then there will be 1 and then. So there will be H of delta in this case. So whatever the error rate in the remaining ones are. So it is minus 1 minus delta, and to do the privacy amplification on the remaining ones as if you're doing it. So it is H of delta, right? Where this H is the Shannon entropy, and it is a binary Shannon entropy like this, right? Between the two. So we use H2 symbol here also, and here also, everywhere it's H2. Okay, so still we can have a positive key generation rate in this case. So what we can do is we can increase the error correction process like this. For example, this is what the key generation rate would be there. So I'm plotting log to the base 10 of R, which means that if I'm sending, for example, this 10 is to log to the base 10 of R to be equal to minus 10 means that if I'm sending 10 is to power 10 bits, I'm only retaining 1 of it. 10 is to power minus 5 means that if I'm sending 10 is to power 5 bits, then I'm retaining in then only 1 of it. But still it's non-zero, right? It's greater than 0. So we have, although the key generation rate is very less, but still we can retain certain number of bits. So if I do this, this 0B and 1B, 2B means that these are the two-way classical communication stuff. So if we only do the one-way classical communication, then we can correct up to this much error. So just ignore this 6 state. I will talk about it when I talk about the more protocols. But if we only do the one-way classical communication, then we can correct up to this error, right? And this distance, I plotted it against the distance. This distance is actually telling me that is coming from this eta detection. So the more the distance is, the less the key generation rate becomes. Because as the distance increases, the P expected decreases because of this eta t over here, and eta t depends on the distance like this, right? L is the distance. So with the distance, this distance L, the key generation rate decreases, right? Which means that there are more errors in it, and now more bits will be lost in error correction and privacy amplification. So if you do only one-way classical communication, then you can go only up to a distance of 25 kilometers approximately. But if you do two-way classical communication, add to it, and you prepare you correct certain errors using this, then you can increase your distance. So there are many steps of it. If you do one step, that is, you compute the addition modulo 2 in one time, and then throw away half and keep the process that I explained earlier for error correction, then of course you can go to an additional distance. And if you repermute them and do this step again, you can go up to this distance. And if you again repermute, you can keep increasing the distance. This is the 20% limit of this two-way classical communication, two-way classical protocol that is known. So this is the distance up to which you can go if you do, if your delta is less than 20%, right? So, and this in this case is in fact for your delta less than 20%, whatever it corrects. In fact, in this case, if your delta over 1 minus delta is less than 20%, this scheme works, right? That it can still you can still correct the error, and you can still generate a non-zero key generation rate. So if in the normal case, when there's no photon number splitting attack, if your error rate is less than 20%, you can have the positive key generation rate. But in the case where where there's photon number splitting attack, where there are the basis known case, so these are the number of pulses and the fraction in which the bases are known, right, in the photon number splitting attack. So in this case, if delta over 1 minus delta should be equal to 20%, then you can of course still retain a positive key generation rate. And you can go up to a distance, up to this distance, for example, in this case, with certain numbers, with certain mu and certain eta detection and everything. So this is the limit that you can achieve with this two-way classical communication type of protocol that I explained earlier. And this is the ultimate limit. This limit is in fact delta to be equal to 25%, for which we do not know the protocol yet. How to correct the errors up to 25%. We do know the protocol for 20%, but we know that in principle, theoretically, you can correct the errors up to 25%. Okay, so this is how we have. So we know certain methods in which we can correct the errors, and we can amplify the privacy. And we can also see that how Eve can take advantage. You can do certain attacks which are give her an advantage in case of low quality apparatus, right? So she can do photon number splitting attack. She can increase the number of pulses for which she knows the basis. She has, knowing the basis means that she has the correct basis as LS and more. And then she can, of course, has more information, but still they can generate a positive key generation rate in that. So all what they are interested in then will be this key generation rate R, that whether it is positive or not. So please, I'll stop here. And in the next lecture, we'll be seeing that how entanglement can be introduced into it and what protocol can be made from that. Okay. So let me see if there are other questions. No, in this case, there's no quantum memory, right? So in this case, there won't be any quantum memory. So the Gaussian is a normal distribution, yes. And in this case, we are not taking the Gaussian because if you are using the weak coherent pulses, their probability is distributed as the Poissonian probability distribution. So the normal distribution is something like this. It is the Gaussian and it is the normal, which is like this, and the Gaussian is this. So it is peaked here and it decreases like this. So it is peaked at n is equal to 0 and then it keeps on decreasing, right? So this is the difference between Gaussian and Poissonian. It is equally distributed about n is equal to 0, but it is not equally distributed about, it is spiked at one end. And then, and you have asked that why in the case of 1 minus delta pulses, the disturbance is not equal to 1. It is because she keeps one of the photon, and of course, in this case, she can keep it in the quantum memory in order to take more advantage of that. If she keeps it into the quantum memory, then she can delay the measurement on her photon to be done after the bases are announced, right? And when she delays it, then the basis are announced, then she measures it at the time and in the same basis as Alice and Bob do, right? Which means that she doesn't create any error. So the qubit is already received by Bob. She hasn't done any measurement on that. She doesn't introduce any error, and she has known the basis exactly, right? So we did in the last case that whenever she tries to measure something, she will introduce error. So since she has not done any measurement on it before the announcement of the basis, before Bob measures it, so it means that she has not introduced any error. So that is why there is no disturbance in it.
Thank you very much. Could you summarize which exercises and quizzes belong to this lecture?
Okay, so this photon number splitting attack may not be there, but some information like when there are laser pulses that are used, then what you can do, what advantage you can have, and some questions like that in there. So this is the quiz 3 in there, right?
Yesterday, we had the 2.2 QKD quiz. Meanwhile, the lecture notes have been included in the quiz, the Jupyter notebooks with the exercises that belong to this chapter, and also the recording. From today's lecture, we will have number 2.3. We will soon also upload the lecture notes here and also the recording within 24 hours. And then you can do the exercises that belong to this and the quiz. Time for a 5-minute break. These have been 2 great sessions. Thank you very much, Aeysha.
Thank you very much, and see you tomorrow, everybody. Bye.
Great, and Aeysha will also share some more resources on the topics via Discord. Hussein, he gave an office hour session this morning, which was very helpful. Thank you, Hussein. Tomorrow, there will also be an office hour by our participants and partners, CQTech. And on Sunday, an additional office hour by Hussein and a programming tutorial by CQTech. If you have other feedback, please keep sharing because we always want to make it the best summer for all of you. We have our 2 team members here, Vardan and Alex, who were really crucial for getting this program together. Vardan, could you share about what is coming up with the software bootcamps the upcoming weeks?
Sure. This week, you are all set up on learning about the basics of quantum computing, which QWorld is like really awesome at doing. But next week, we will dive into a bit more specifics. So we will be learning on the various software bootcamps, and these bootcamps are being offered by the various leading quantum industries right now. So we'll be having one from Xanadu, we'll be having one from QEra, and plenty others. It is really important for you to attend these software bootcamps if you want a chance at being recruited for the Quantum Solutions Launchpad, because these bootcamps will offer you specific skills. It's not like a general knowledge about quantum. These are very, very specific skills which can be really useful if you want to step into the industry. Even if you do not want to participate in the Quantum Solutions Launchpad and you are trying to get into the industry of quantum, maybe get in the career fair and get hired, again, these software bootcamps would be really, really useful for you.
Thanks, Vardan. Alex, together with Aeysha and Madalena, you have been organizing the hardware lectures and virtual lab tours. Can you share more about that? What can we expect in the next few weeks?
For the next weeks, you will be diving more into the quantum hardware. This week, we have been speaking a lot about the quantum algorithm, quantum computing, but next week, we will start looking at some other qubit platforms. We will have 5 qubits that we identify for this program. Of course, there are some other techniques or other approach to make the qubit, but for this program, we will focus on superconducting qubit, the trap ion, with some ion Q, and also you will have some virtual lab tools. Some companies that accepted to showcase their lab and also what they are doing and how we can control and also read out the qubit, the set of the qubit using this platform. We will also have some quizzes that have been prepared for this lecture so that we will go deeper to understand exactly what is going on in this platform. Yeah, that's what we will have. Also, there will be a hardware panel discussion that will explore some qubit modalities and also the roadmap, the challenges. So you will have also the opportunity to ask some of the questions here to understand exactly what is each company are doing. We have 2 sessions of the hardware panel discussion. The one is 19 and the other one will be in 25 of this July. Yeah, that's it for the next 2 weeks.
You can check the schedule, womanium.org/quantum/schedule for the exact dates. For Dan, there are some questions about the software bootcamps. Are they accessible for everyone in any country?
Yes, absolutely. As we have mentioned time and again, we focus on building a global quantum workforce. So yeah, any country, any time zone, any nationality, you're all welcome.
Then 1, are there any prerequisites regarding software? And 2, are the bootcamps suitable for beginners?
Honestly, I wouldn't say they are very beginner friendly. They have a very specific focus on various topics of quantum. So yeah, if you are completely new to quantum, they might not be the best fit. Like, but if you are already attending the various courses by QWorld, if you have a Q Bronze, Q Silver, and maybe Q Nickel, or if you have been following very diligently throughout this week, then I think you should be on the right track to attend these sessions. About having prior requisites about the software, Python should be good. Any mathematical skills that you have should be sufficient. If you do have good knowledge of quantum platforms like maybe Qiskit, Penny, it's very good.
We really look forward to those weeks with all of you. The hardware is currently where it really happens, where the difference needs to be made, where also the bottleneck is right now. And then we can execute everything that Gibran is teaching us and that you will be teaching right now.